Welcome back to another fun and exciting Q&A episode of Space Nuts. I am your host for this episode, Heidi Campo, and joining me is Professor Fred Watson, astronomer at large.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Fred, how are you on this fine day?
I'm very well, thanks, Heidi. And I'm delighted to see you again because it is always a pleasure to take our listener questions, especially on a nice, fine, what is here in Australia, winter's morning. It's a sunny day, as we often get in wintertime in Sydney.
Well, you'll be delighted to hear that it has finally stopped raining here in Houston, Texas. The sun has come back out. I was starting to forget what it looked like. But we will be going camping this weekend. So I'm looking forward to that. I will report back to you guys next week what the weather from West Texas looks like.
If you get any great photos, Heidi, we should try and post them on the Space Nuts website.
Oh, maybe I'll have to bring my telescope and do some astrophotography out there. Actually, I am gonna do that. And speaking of the United States, all of our questions are from the U.S. this go around, and our first question comes from Dean from Washington D.C. Doesn't get any more United States than that.
Yeah.
Dean asks, "Are all neutron stars pulsars? If so, is it not theoretically possible that a collapsing star has so little angular momentum that it doesn't pulse? If not, what else can a neutron star be?"
So, this question has a simple answer. No.
Thank you, Dean. Moving on.
Yeah, I might elaborate on that a little bit. Not all neutron stars are pulsars. And actually, look, I'm going to take a direct quote from a NASA website called Ask an Astrophysicist. Doesn't come any better than that. Because I love the opening of this little answer. Most neutron stars in the universe are old enough and tired enough that they are no longer pulsars. And let me just interrupt that quote by reminding us what a neutron star and a pulsar is. A neutron star is this highly collapsed object. It used to be a star, but now we're seeing the collapsed core of the star only a few kilometers or miles across. What makes it a pulsar is when it's spinning rapidly and beaming radiation from its magnetic poles. So they behave just like a lighthouse, flashing on and off, pulsing, as the name implies. So Dean's question is a good one. Are all neutron stars pulsars? And they're not. And as the NASA website says, most of them are old enough and tired enough that they're no longer pulsars. They've stopped spinning. And just one further sentence on that, which I think is quite illuminating. A recent paper estimates 1,000 million, what we call a billion normally, 1,000 million old neutron stars in our galaxy, even though the known number of pulsars is only about 1,000. So there are many, many more neutron stars that don't pulsate than there are that do, just because they've lost all their rotational energy. So a great question from Dean, sent me to NASA's website, which is always a good thing.
I think they know the right answer.
One would hope so, yeah.
I saw a T-shirt in their gift shop a few weeks ago when I was there, and it just said, "The Earth is round, we checked. Love, NASA." I thought that was kind of cute and cheeky.
Yeah, I like that one.
Our next question is from Ben, who is actually a new listener. So thank you, Ben, for writing in. This is so much fun. Ben says, "I came across the podcast last week and I've been zooming through it. I love the content. Thank you." And then Ben goes on to say, "I've got a question and hopefully you haven't already answered it on the roughly 450 episodes I haven't had a chance to listen to yet." But he says, 1, when neutron stars and or black holes merge to produce gravitational waves, they lose mass, which gets converted to energy, which comprises of the gravitational wave. But how does that conversion work? Specifically, I'm thinking of a binary neutron star system merging. Since my understanding is that the mass of the neutron is quite consistent across the universe, a reduction in mass would imply that a reduction in the number of neutrons would imply a reduction in the number of neutrons. If this small leap of logic holds, what determines which neutrons get converted to energy? Are the faded neutrons extracted evenly from throughout the merging objects, or is there a region that seems to be favored? And what does this process of converting neutrons to energy look like? Ben is curious and hungry for answers.
It's a fabulous question, Ben. I've got a question for you, Ben, as well. How did you manage to get through 450 episodes in a week, less than a week? That defies probably the laws of physics, I think. But that's all right, because apparently merging neutron stars also apparently derive, they break the laws of physics. So, Ben, your question, as some of our listener questions often do, because they are so good, sent me to the World Wide Web. And the answer to this question is it's quite subtle. And there's several things going on, partly because we're dealing with very intense gravitational fields. And to answer your question, are the fated neutrons extracted evenly throughout the merging objects, or is there a region that seems to be favored? That probably relates to the event horizon of the neutron stars, because they do have event horizons. And I don't think I'm capable of answering that question. And in any case, it's a more subtle than just neutrons getting thrown away than what your question might imply. So I would actually suggest, Ben, that you have a look online at the physics.stackexchange.com website, because physics.stackexchange.com has got a very nice set of question very similar to yours, and some quite lengthy answers that go into some detail and look at different aspects of this question. So if you Google energy conversion from mass to gravitational wave, that will take you to this website. And maybe I can just talk about one of those answers, and that is that if you imagine one of the sort of subatomic particles, and what we call an alpha particle, which is the nucleus, a helium-4 nucleus, got 2 protons, 2 neutrons, but its mass is actually less than the sum of those protons and neutrons. And that's because there is something called binding energy that's released when that particle is formed. And so the bottom line here is that mass and energy are highly interchangeable when you're talking about the kinds of things, the sort of extremes that we are looking at in the case of a neutron star collision. Even in a neutron star doing its thing, it's still extreme situations. And because of the relationship that we're all aware of between mass and energy, E equals mc squared, that is why you've got this potential to transform what looks like a mass of a single particle into energy to result in a lower gravitational mass for the pair of neutron stars. Sorry, the bottom line here, which I should have said at the beginning, is that often when you've got this neutron star collision, you get a gravitational wave which essentially has enough energy to account for a difference in mass. It's not just the sum of the two neutron stars that come together. There is a mass loss as well, which we see as the gravitational wave. And this is one of the mechanisms that causes that. So have a look, Ben, at that webpage. And if you still don't get it, ask us again, and I'll have another shot at it. But it is a really interesting question, and a good one too. It got me thinking. Yesterday I was worrying all day about this question, trying to take my mind off the root canal treatment that I was having at the dentist at the same time.
I also think of particle physics while I'm at the dentist.
It's the only thing to do, really, isn't it?
So I will give my dentist a shout out. My dentist was one of my good friends in doing my undergrad, and it was kind of cute because the whole little cohort of us, we were in a powerlifting club in my undergrad.
Okay.
And we were just a bunch of kids, and now he's a grown up who's a dentist, and we're all doing our things. One of the other ones went on to be a neurosurgeon, and so I'm like, it's quite a little brainiac group of strength athletes that went on. So shout out to Dr. Gatlin Marks, dentist at Platinum Dentistry in Utah. That's unprompted, not paid for, free advertising, but he's great.
Well, I should advertise mine, shouldn't I? It's nothing like as nice a story, but I won't bother. No.
0G, and I feel fine.
Space nuts.
Well, our next question is an audio question from Craig, and we are going to play that question for you right now.
Hi, professors. It's Craig down in sunny Merimbula. I've been seeing items about James Webb seeing really massive galaxies, much bigger than current cosmology expects. Are we in an older universe? Could we tell the difference between a Big Bang and a supermassive white hole that's erupted into an existing space-time? Just an overactive imagination. Hope you're enjoying your week. Ciao.
All right. That was Craig's question.
Craig, the only person asking a question this week not from the USA. Okay, his question about big galaxies. Is it telling us that the universe is older than we think? Maybe. It's a nice way of thinking about it, except that we still, all the evidence points to the universe having a beginning, which was 13.8 billion years ago, which we think was the result of an event called the Big Bang, an explosive event. We believe that's the case partly because of what we observe today, but we can also still see the flash of that Big Bang by the fact that the light has taken 13.8 billion years to get to us. So it's very hard to see how, if the universe was older than that Big Bang, how galaxies would survive that explosive event. What Craig's question is about is, are there galaxies that are older than we think the universe is? And it defies logic. It's like saying, and in fact, for a while, this was one of the problems with the Big Bang theory. People thought the planets, stars, and atoms were actually older than the measurement of the age of the universe that we got. And that was one of the problems for the Big Bang theory, which was only really resolved in the 1950s and 60s. So I think that's still a step of logic that we're not prepared to dismiss. That yes, there is that. The Big Bang does mark the start of the formation of galaxies and the galaxies in the universe. I have a colleague and friend who's a very distinguished astronomer in the UK, Richard Ellis, and he is absolutely. He's a cosmologist. He's somebody who looks at the history of the universe, very interested in the history of the early universe. He is absolutely certain that those galaxies that we can see that do look bigger and older than what we expected them to be, that they do not defy conventional cosmology, that we can still work out theoretical models that would allow those galaxies still to be young, even though they look more advanced in years than we thought they would be. So it's all about our understanding of galaxy formation rather than having the cosmology wrong, rather than having the age of the universe wrong. So a good suggestion, but I think we are still stuck with trying to understand how these galaxies got so big so quickly.
And stuck is what it is sometimes. There's that's what I get excited about with space. There's so many questions that have to be answered. Other sciences are so defined, but space is infinite for us to figure out.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Our last question is from another curious listener. Mark from Bloomington, Indiana, says, "Hello there. What might meteors look like to a person on the surface of Mars or Venus, if that were possible? The planets are at extremes of atmospheric density, but carbon dioxide is the primary atmospheric gas for each, and there is very little oxygen present. Compared to Earth and to each other, would meteors appear brighter or dimmer? Different colors, travel faster or slower, more or less likely to be seen given the thick or thin clouds and the clouds' altitudes, more or less likely to strike the surface? Thanks for any insights or even guesses."
I think we've been sprung here, Heidi. People have realized that we just take guesses at these things. So it's another great question. You know, I think none of the questions that we've had today have ever come in before. Maybe people have been speculating about the mystery of these early galaxies. But this is a great question. What would meteors look like to somebody? Let's just stick with Mars for now, because that's the easier one to deal with. I think Venus will be a problem because the atmosphere is so thick, so opaque, that you probably wouldn't see any meteors at all, just because there's very little transparency in the atmosphere. Mars, however, is different. It does have clouds, but not as many as we have here on Earth. Let's get to the easy part of this question, which is Mark's query: are they more or less likely to strike the surface? And the answer is they're more likely, because Mars's atmosphere is much thinner. It's less than 1% of the pressure of the Earth's atmosphere. That means that it's more likely that a meteoritic object would survive its passage through the atmosphere to reach the ground. So, and we do find meteorites on Mars. There are many examples that the various Mars rovers have found meteorites on the planet Mars. A meteorite is a meteor that's got as far as landing on the ground. But what they would look like in the sky it doesn't really have that much to do with what the constituents of the atmosphere are, because what you see when you see a meteor, a shooting star, is the fact that it is simply it's being heated up to incandescence. It's not burning in the sense that, things burn in the presence of oxygen, and that, I think, is the thrust of Mark's question. But what you're seeing is this thing shooting through the atmosphere. It is meeting a gas. The gas is providing some resistance, but also a lot of friction on the outside of this particle or stone or rock or baseball, whatever it is that's coming in, whatever size it is that's coming in. And that's what causes the brightness of the meteor. It's being flashed into incandescence by its speed, rather than a chemical reaction taking place that would make that much difference. Although certainly we do see, evidence of the oxygen in the light of some of these. So meteors on Mars would look similar to what they do on Earth. There's some dispute because the atmosphere of Mars, whilst it's also much thinner than Earth's atmosphere, is distributed differently. The way in which it falls off in pressure as you go up in height is different from what it is on Earth. So that might mean that the height at which meteors start to glow as they come through the surface, come through the atmosphere of Mars, might be different. And if they were lower, if they were burning up lower down in the atmosphere, then they would look a bit brighter than they do here on Earth. If they were burning up higher in the atmosphere, they would look a bit fainter. And it's not quite clear which of those is the case. There's some dispute among certainly the things I've read about whether they will be brighter or fainter, but they will be much the same. So we hope that maybe one day when astronauts are exploring but not colonizing Mars, that they might send us back reports of meteors that they've seen in the night skies of Mars. And maybe you'll hear about it on Space Notes.
Maybe so. And it is my understanding that is one. I mean, there's so many concerns with Moon to Mars missions and a potential Mars colony. It's not as safe. Our atmosphere does surprisingly a lot to protect us. And that is in a lot of student design competitions, that is something they're really asking for students to look at is, hey, how can we protect potential analogs or colonies or any other assets we put on Mars? How do we protect those from these constant impacts? And that is really kind of an interesting question right now. And that's not really my wheelhouse, but people in the engineering world are there's a lot of fun things for them to do with those projects.
Indeed, that's right. It's a different world from ours. It's everything's different. Radiation, meteoritic bombardment, all of those things, low pressure, low gravity, different world, and a lot to think about if we are ever going to have humans walking on Mars.
All right, Fred. Well, this has been another fantastic Q&A episode. I love the way you answer these questions. I feel like every time we write in, I feel like each one of us has an opportunity to be a collaborator with you and gets to experience what it's like to be on this intellectual journey together. So keep sending in your amazing questions. You guys are half of the brilliance of this show. So thank you so much.
That's right. I agree there wholeheartedly, Heidi. At least half, in fact, maybe more than that.
Excellent. Well, thank you everybody to listening to another episode of Space Nuts. We will catch you next time.
Sounds great. Thanks again, Heidi.
Hi, Fred. Hi, Hugh. Hi, Heidi. It's Andrew from the southwestern Indian Ocean. We've just finished a 7-day crossing of the Indian Ocean and stopped yesterday at the beautiful island country of Mauritius. And it's winter there, but the temperature was in the mid to high 20s. So, if that's winter, I'll take it. It's been beautiful. The seas were quite smooth after our treacherous rounding of southern Australia. But now that we've left Mauritius, we're heading into some heavy seas as we move towards the Cape of Good Hope and then come up the other side of Africa. But Mauritius was absolutely beautiful, lovely people. Interesting story behind Mauritius. It's an island that was discovered by Arabian sailors. It was unoccupied, so they moved in, and of course they brought their slaves with them. Somewhere along the line, they handed it over to the Dutch and the Portuguese. The Dutch kind of decimated everything they possibly could. My wife's half Dutch, so I've got to be careful what I say. But they killed off the dodo bird. They destroyed most of the forests. They killed off the native giant turtles. Nothing like that is there today. But then the French moved in, and they stayed there for a very long time until they were tipped out by the British, and the British held sovereignty over Mauritius until independence late last century. Beautiful country, very rugged volcanic landscape. Saw the volcano at the top that still exists. It's dormant. It hasn't erupted for a long, long time, and I hope it doesn't because it's got houses all over it. Just a beautiful landscape. They speak French, and English as their predominant languages, but the native people who are originally, from the slaves of South Africa, speak French Creole. So it's really, really interesting mix of people, but a lovely country and very, very much worth visiting, and a very big Hindu population as well. And so we visited a Hindu temple and the sacred waters that were discovered by a Hindu many, many years ago, where people were blessing children and walking through the waters, which are just as sacred as the Ganges, apparently. There was a little monument there to the sun and the planets. So there was a little astronomical connection while I was there. Anyway, that's where we're up to. Next stop will be Cape Town. It's going to take us 5 days of sailing to get there, so I'll report on that next time. So, hope all is going well with Space Nuts. See you soon.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.